Welcome, everybody, to UNT Alumni Live. Thanks for being here. I am Claudia Taylor with the UNT Alumni Association, and welcome to this week's episode. Today, we are shining a spotlight on UNT's incredible Center for Agile and Additive Manufacturing in the College of Engineering. You might be asking, what exactly is additive manufacturing? In a nutshell, it's 3D printing. And today we're going to see how this hub of research and learning, founded thanks to a $10 million appropriation from the Texas legislature, is leading the way in creating innovative, collaborative applications and training the next generation of engineers. We're being joined today by Regents Professor Dr. Narendra Dahotre, the center's leading founder, as well as Dr. Muntry, manager of CAAAM, and UNT College of Engineering Professor Dr. Banerjee, who will lead us in a tour. Before we get started, just a few reminders. If you're joining us on Zoom, please keep an eye on the chat section at the bottom of your screen. I'll be posting some useful links there, and you can also use that to send me your questions. I'll also post a link to a survey. As always, fill that out and you'll be entered to win a UNT prize pack. If you're watching on Facebook, you can also leave us your questions there in the comments section, and we'll get to as many as we can. Now, before I hand the program over to my colleague, Casey Kamenetsky, let me tell you a little bit about the UNT Center for Agile and Additive Manufacturing. Additive manufacturing, a process that builds 3D objects through the layering of metals, ceramics, and alloys, is an emerging technology in high demand from a wide range of industries. It's capable of producing higher strength and more energy efficient materials. But before it can be used far and wide, we need to gain a better understanding of the science and the processes that make it work. That's where UNT's Center for Agile and Additive Manufacturing comes in. This state-of-the-art laboratory allows UNT faculty and students to conduct hands-on research and dive deeper into the complex world of 3D printing, helping show the nation and the world just what we may be capable of doing far into the future. Doctors, thank you for being here, and Casey, take it away.
Thank you, Claudia, and thank you for joining us, Dr. Dahotre. Listen, I know we have a ton to cover, and I know we won't get to it all this hour, so I want to jump right in. Can you just really break down what 3D printing is?
Yeah, 3D printing is the way you say it is. You know, you are printing any object in a three-dimensional manner, basically. Think about this way. 3D printing is a extension of what you have been printing using your laser printer in your office or in your study room. You give the command to the printer, and printer head start moving around and print letters. So imagine that you keep printing letter up above letter continuously. So what will happen after some time? That letter will start wearing a three-dimensional three dimensions, basically. But it takes a longer time to do that. So imagine that 3D printing, what you do in your office or in your home study room, is you are injecting the ink through the inkjet printer and printing the letters. So you replace that ink with something else which is in liquid format. Most of the materials which are in nature do not exist in liquid format. So what we do is, if we convert them into liquid format and inject the way we inject the regular ink onto your paper, we should be able to print any other material too. So that is what this 3D printer does. It starts with the materials like polymers, metals, ceramics, and take them and melt it before they are injected. So we convert them. So that one additional process is added into the 3D printer. What you have at home is already you have an ink which is in liquid format, so you don't have to melt it before it is printed. In our 3D printer, what we have is a raw material, which is oftentimes a polymer material, metals material, or ceramic material, which do not exist in a liquid format at a normal temperature. So what we do is we take that material, and before injecting them through the injector, we melt them. That machine has a capacity process which melts that material and then injects it. Then the rest of the process is same as like your inkjet printer, and we keep doing that one after another, keep doing that one above other, same thing. And that's how we build the 3D printer. Before we do that, also one step is there, we have to make a drawing of what you want to print, and that's where you must have heard the CAD drawing, CAM drawing, computer aided designing, so most of high school students and college students know what is CAM means, CAM drawing and all those things. So you make the drawing what you want to print, and then that is the one we feed into the computer. What it does, asks the computer to move that injector in that particular shape and size, while it is injecting the liquid metal or liquid ceramic. And then it prints the way the drawing is, So after a few hours, you get a final product made out of 3D printer, that's what it is. But it does in layer by layer. So typically each layer is a fraction of millimeter. So imagine to print a 1 inch or several inch tall component, it needs several layers, So oftentimes thousands of layers are put together to build one component. That is why it takes longer time, and all during that time, you have to keep the raw material come into the machine, and the raw material has to keep getting melted same time. So that's why this process of 3D printing of metals and ceramic becomes much more complex and much more difficult than what you see in the market, which are oftentimes the polymer-based printer. Now, what is the difference between polymer-based printer and metal printer? As you say, that polymers melt at much lower temperature, so the handling becomes much easier, whereas metals and ceramic melt at thousands of degrees centigrade. So the melting process is a very complex process, and that makes these machines very special and difficult to handle, So basically, but the principle is same in what you have in your office or in your study at home. What printer you have is the same type of principle we use in 3D printing of the metals and ceramics, but added component is the melting unit, which is built into this 3D printer, which melts this raw material. That's how the 3D printer works.
Well, that is fascinating and makes perfect sense. This seems to be a fairly new and trending technology. Can you tell us about how long this has been going on, and why are you so fascinated with it?
Yeah, the fascination is because let me go as back as maybe 30 years back, when I was a graduate student at Michigan State University. My professor walks into my office and he says, "Hey, I want to try something new." What he wanted to try, because he had talked to his colleague in electrical engineering department who used to work with the lasers. They were using lasers those days for diagnostic purpose. They were using lasers for the communication purpose, and they were used by the Department of Defense and NASA for the communication, for diagnostic in the space. They used to shine the laser beam into the space, and that laser beam get reflected back, and by reflected beam they used to diagnose the different kind of objects in the space. So that is what they were using lasers. But at the same time, those laser beam have a tremendous power in it because of spatial light beam. So my professor said that, that these people, when they do diagnosis, they just are not using that power associated with the laser. Why can't you use that power, for something else? And he thought that that power can be used for melting the materials, which has a tremendous power in the beam. So he said that let's take that power and start melting the material, and can we drop that material in a controlled fashion on the substrate. And we did. Those days we had old lasers, so I took that old laser and built a motion system. This is the early 80s. We did not have PCs those days. We used to have computers and mainframe computers, so we could not use those computers. So I designed a mechanical system which would move in X and Y direction, and I mounted the laser head on it. I mounted the powder injection system on it and moved few inches around, and started depositing the few millimeter thick layer, so that way I could cover the substrate material. And my purpose was to take a simple, low quality, soft material and coat it with a hard material to give the hardness to the material, to give the better wear properties. So I could build about maybe 4 or 5 millimeter thick layer on the top of the substrate, And that's what I kept doing and started looking into the material properties and so on. So those days I was already doing the additive manufacturing process, but not building the entire component, just building few millimeter thick layer, and that has been my area of research, and then what happened, it picked up that area picked up by many other researchers. They started looking into it in more detailed way. And one group from one of the national labs in New Mexico, they thought of this process. Can we extend this process to even depositing even several inches thick layer, and they were able to do, because that was the time, it was early 90s. By then PCs have been in use and more sophisticated motion systems came into existence, and they were able to now not only deposit the straight flat layer, but they were able to deposit much more complex shapes, and that's how the 3D printing came into existence in the early 90s. And though that group of people even coined this word 3D printing, but it has been in existence even prior to that, and then I said, oh my God, if I had thought a little deeper and better, I could have called it my work as a 3D printer in the early 80s, so I missed the boat, doesn't matter, so now it has picked up. 3D printer has become what it has become today. It is because of sophisticated computers and sophisticated motion systems, which allows us to deposit the material in a very complex fashion, So that's how the 3D printing came into existence in a today's form,
To think that you were on the front edge of this groundbreaking technology, developing these tools and skills is simply remarkable. While I'm playing with Cabbage Patch Kids and Rainbow Bright dolls, you're playing with lasers and changing the future. I mean, this is remarkable. So that is really exciting, Dr. Dahotri, and what an honor to have you at our university now. And starting CAAAM and getting this facility up and running so that our students can now be trained on this cutting edge technology. So at this time, I know that we have our colleague Daniel is over at Discovery Park in one of the classrooms there. So Dr. Dahotri, can you kind of tell us a little bit about what we're about to see and what room we are in?
Yeah, Miss, what happened, Miss, we were able to, this technology has been developing in a very rapid space, not only material scientists, but mechanical engineers, electrical engineers, and computer scientists, everybody is involved in this process, So it is expanding and getting developed in a very rapid pace. In a process, what I call it as this, the way this technology is developing like putting a cart before the horse, So there are a lot of things have to be yet to be looked at to make this technology more useful for the many applications, It is very fascinating, but it does not do what it's supposed to do yet, So what we have done is we have gone to the state of Texas and asked them to help us to do that, and then we were fortunate enough 2 years back, state of Texas legislature listened us and understood us, and they gave us $10 million to first 2 years to develop this technology further for better understanding. But as a part of that, what we propose to them that we will not only develop this scientifically, technologically, but also we will develop for the use of the common people, because eventually this technology is going to get into mainstream manufacturing, So it is a little bit further, a little bit further down the road, but it is going to happen. So when it happens, we have to be ready and prepared. So in order to do that, what we have done is as a part of this center, not only focus on the research aspect of this technology, but also educational aspect of this technology. And as a part of that, we have established Institute for Transformative Education in Additive Manufacturing, what we call it as an I-team in short, and that as an I-team, under the I-team, we have been setting up this infrastructure to have training, education about this technology, and where this Professor Raj Banerjee is standing and Dr. Mantri will be showing you is the I-team location, where the people can come in and get education, get the educational part of this technology, and also have some hands-on education about this technology. So what they will show you is these are the equipment which are easy to handle, easy to work with, and they are mostly dedicated for the polymer-based material printing. So they will show you how where to start and how you end up getting this component printed through these machines. So with this introduction, I think I will give it to the Professor Raj Banerjee and Dr. Mantri, who will explain you further what this lab is about.
Wonderful. Thank you, Dr. Dahotri, and welcome, gentlemen. Thank you so much for making the time to be here and show off our really incredible facilities. So let's start with the cute little guy that we saw on the screen there a second ago. This looks like a rendering of a baby Yoda, if I'm not mistaken. Is that correct?
Yes, that is correct. This is actually, as Dr. Dahotri was mentioning, every single 3D printed object will start with a computer-aided design or a CAD file. The term CAD is used quite commonly in the common parlance, that's why I'm using it. And then you can use that starting point of taking a standard software, which is for AutoCAD or SolidWorks, to design your file. Because the way 3D printing works is you are first conceptualizing and designing the component, or it could be a sophisticated aerospace component, or it could be a baby Yoda. Whatever you want, you can actually design in the software. And this is showing you a prototype design of that type. And then the software will effectively do a virtual building of this part. And we'll show you an example of how that virtual building, not the real building, layer by layer will take place. Because the software will take this digitally, slice this kind of a component into many layers, and give you how, when you take it to the 3D printer, will it be built in a layer by layer fashion. So if you move on to the next computer, do you have that? Oh, that's not working all the time.
You can show it on this.
Yeah, sure. But this is again another part, which is the I guess the Falcon, Falcon from the Star Wars thing. So again, these are the different. One of the points that we are trying to make here. So I think Mantri has pulled up the way the software would work. Yeah, you can see that it is the same baby Yoda. Actually, it's as if you're looking at layer by layer of how baby Yoda will be built in the machine, and that's what is dynamically going to happen when you try to build that. So again, these are just simple examples that everybody can relate to. But the idea is that, of course, you're really not building baby Yodas for an application. It is just for fun. But this is what the students love to do when they first start getting exposed to 3D printing, because this is something they can relate to, and it's something that they can learn for fun. And this can go not only to our undergraduate students at UNT, but also down to high school students. And they get excited to see these things, because if we sort of bombard them with parlance on sophisticated components for industry, they will lose interest. So that's the idea. Anyway, coming to the real machines, I think what Dr. Dahotri was already mentioning, most of the machines that we have in this particular lab are actually systems for polymer printing or plastics. So you're printing in 3 dimensions, these complex plastic shapes. An example is going on in one of the machines right now, as you can see here. Yeah, so this is effectively like a fan blade. You can see the fan blade after building. It's the same fan blade that is being built layer by layer, made of a plastic or a polymer. So this is the logic. There are 4 or so systems of that type. And I can also show you how it all starts. It starts with these filaments. So if you can see this is the plastic wire, you might call it. We call it a plastic filament. That is going to be the raw material that is eventually going to be printed in the 3D printer to give you that complex shape of what you're building. I will also briefly introduce the other educational printer we have here, which is a metals 3D printer. Now, again, as Dr. Dahotri was mentioning, metals 3D printing is a completely different league of 3D printing as compared to polymer 3D printing. Polymer 3D printing has actually become very common now. You can get desktop printers for your own home for prices less than $500. Having said that, the ones we were just showing you are a little bit more expensive because they're laboratory scale equipment, but still we're talking of thousands of dollars. as you go to metal 3D printing, so just to give you an idea, you're talking of 2 orders of magnitude more because this printer is about $250,000. So it's $250,000. Why? Because again, the technology involved and the sophistication involved in metal 3D printing is much more. Having said that, our objective under the Institute for Transformative Education in Additive Manufacturing, or the educational wing of CAAAM, is to expose the students not only to the polymer 3D printing, but also the metal 3D printing. And that's why we have invested in getting one of these, what I would say, base level metal 3D printer. And the technology in this will be clearer to us when we go over to the next lab, because this is also built on the same system as powder bed, laser-based powder bed printing. So again, we talk about that when we go to the more sophisticated type of this printer, which is our research machine, but they are broadly called selective laser melting or laser-based or laser powder bed fusion systems. Okay.
Dr. Banerjee, if I may ask, with this 3D printing, are the materials, I guess, sturdiness, is the structure compromised in any way, or are they still as sturdy as being built the old-fashioned way, if you will, depending on whatever these components end up being?
Right. And that's a very, very valid and a good question. So it's good that you brought it up, because the way I would put it is, if you take the whole gamut of 3D printing of plastics or polymers, then the technology has evolved to the point that you are able to reproduce largely the performance and the properties of what you would do, say, with injection molding, which is a commonly used industrial technique for plastics, for shaping and making complex plastic shapes. You can do the same thing with 3D printing, in other words. So it's almost there, let's put it that way. But it is far from there, and that's an honest answer, at least from my perspective, when it comes to metal 3D printing. We are getting closer to what a conventional industrial process for metals, like forging, rolling, extrusion, rod processing, all these things which we broadly call thermomechanical processing. To put it simply, heat and beat up the metal. Right? If you heat and beat up the metal, that's how we make complex metallic parts today for real life applications, for engineering systems. That, if you compare those parts with parts made by metal 3D printing, we get the same reproduction of the outer shape. In fact, it could be an even better reproduction of the outer shape, because the printers work great to give you a beautiful shape. But what is still lacking is our understanding of what is happening inside the component. What is the structure? How are the, all the way to how the atoms are arranged? What are the defects? There are often these gaps or pores in the material. And yes, these problems still are there. So can we actually just print a component that we were making all these years by a conventional, well-established process that may be 50, 100 years old, and just reproduce it directly by metal 3D printing? You can reproduce the shape, but the properties are a question. That's where we are. But the technology is constantly evolving, and we are getting closer and closer to that point where we can substitute what has been conventionally made with metal 3D printing. So that would be my take on it at this point.
That is really fascinating. And thank you for being transparent on that. I think that that's really important. And we've seen now that 3D printing has evolved so much over the last 30 years. So this may be a question for any of the doctors in the room there. Does anyone have a prediction on how much longer it will be until these can be reproduced and have the same properties, and we can be confident in the materials that are being produced by a 3D printer?
So, I will let Dr. Dhaotre add to it, but I would say that, instead of giving an estimate of a number, the way I look at it, it is going to be driven by specifics of the component or the material you're working with, to an application driven. For example, even in the domain of materials, I would say our understanding of things maybe with stainless steels, which are very common used metals, as all of you have heard, is better. But you go to some of the other classes of metals and alloys, we have poorer understanding. But even in stainless steels, are we there in terms of routinely producing things? Probably not there yet. I'll give you a simple example of not a steel, but a high temperature material that GE has promoted in a big way, and they have been advertising are these nozzles for the rocket engine, the nozzles that are made with 3D printing. So again, one component, they have brought it to a real production scale and is being used. honestly, even if you go to that GE component that has been so advertised and hyped, you find out, and I found this after discussing with people directly from GE, it's not like the entire nozzle is really 3D printed. It's only certain parts of it that are 3D printed. So that's all. So these are baby steps, and I let Dr. Dhaotre add his insight.
Yeah, so basically it is very mature technology in terms of what aesthetically you can get in terms of shape and size precisely, but it's not mature enough to get what is inside in terms of microstructure which you produce by doing this technology, because the microstructures which are produced in this technology are the one which control the properties of the material, and that understanding is lacking. But as you know, that common person get very impressed by the outside look, what you can print shape size is same as what is conventionally done. So what is left there? Yes, there's a lot of things to be left, because the component produced by conventional manufacturing way will look same as component produced by 3D printing. They will look identical, but the properties of the 3D printed components are not same as the conventionally manufactured component. And that is why they are not going into the actual machine or applications, So, and that is because the methodology to produce these two components by the conventional technique and by this 3D printing are totally different. Conventional methodology involves a lot of different techniques to produce a final component, whereas the 3D printing technology starts with a one raw material and with a one technique, one printer, they produces the final component. So obviously the microstructure produced in these two ways are totally different. That's why the properties are different. So how do we? So that is why this technology needs some more development, to a more understanding. How do we create inside the component what is needed for that component's application? And that is what we are into the business of, and that is how we convince the state and many people who are working with us from the industry side. We can help you do that. We understand, or we feel that we understand how we can make it better, or how we can make it what it's supposed to be made for,
Right.
So that is why we are in this business, and we are different than many other printers, basically, to be honest with you.
Well, and that is absolutely fantastic. And it makes perfect sense, actually. I understand that. So do you think that we're looking at another 30 years to get there, or do you think it will happen sooner than that?
I don't think so that it will be that long, is if we get enough support the way we have been given so far. It's not only we, but there are some other people also looking into this. Now people are understanding it. That's where we want to go, because
Sure.
this big industry like GM, GE, Boeing, all those need these components to be put into their machines, and this is the best technology to make them. They understand. So those are coming on the board. Okay, so people like them, along with the federal government or state government, continue to help us to do that. It is not going to be that long, and that realization has come to everybody's mind, to the industry's mind as well as to the government mind. Just by printing something look what it's supposed to look is not going to help us. It is too much investment to do that.
Right.
So by adding some more investment, we can make it happen. We can make it, use it into the application. So I think slowly it is going to gear up into much more higher speed in terms of development of this technology to actual application. And my feeling is, and I'm always optimistic about it, I started this, as I told you, 30 years back, and within 30 years, it came to this level. So it should take less than that, probably, another 20 years, maybe a decade and a half, we should be able to start putting these components to actual applications, and we will have enough understanding to do that. That's what my feeling is.
That is really exciting to think that we could see this evolve in our lifetime and start changing industries as a result. So that's very exciting. Tell you what, let's get back over to the classroom and take a look at another machine and see what you guys have there.
Sure. Hi. So just continuing on what Dr. Banerjee was mentioning in terms of this being the raw material which we use to print on the polymers. But when it comes to metal, there are some machines which use some kind of metal wires. But for this machine, what we are using is actually a metal powder. I don't know if you guys can clearly see this one, but it's a very fine metal powder, which is usually in the size of about 10 to 45 microns.
This is the metal powder. Yeah.
So that is actually all powder. Let me just kind of slightly disturb it so you guys can probably see it more clearly. But
he's using a brush, so you can see it's metal powder.
It's
very fine metal powder. I mean, to give you an idea of the size, you're talking of a size of about 50 microns or below, which would be, I would say, the thickness of a human hair is about 60 microns. So each powder particle is like a hair thick.
Wow.
So the slight difference is, so you have this machine, there's a laser right above it, which actually does the printing on this machine. So there's also some machines which use different sources of heat generation, but this uses a laser, which is about 200 watt laser. So as I was mentioning, that's why it's cheaper compared to the other machines, which we will show you.
So let me interrupt you. So what you saw is a powder bed. It's a tray of powder, packed into the tray. And the laser beam comes down from the top and moves in a different manner, and wherever laser moves, under that laser, the powder particles get fused, so it's like taking a pen and writing on the paper. So basically laser beam is coming and writing onto the bed of the powder,
Wow.
But the difference is when that laser has a tremendous heat energy in it. So when it's writing on the bed of the powder, it is also melting the powder, fusing the powder, and when the laser beam moves from one location to another location, the melted powder get solidified. It instantaneously freezes down, and forms consolidated material. So that's how you write and create a layer. Once that consolidated material is done in that one layer, that bed shifts down, so the consolidated layer will go down and loose powder will come on the top of that. And then you repeat that process again. The laser beam will be turned on and again it will write there. And you keep doing that, and layer by layer by layer, you build that one. So in the end, you pull out the component out of this loose metal powder, basically and that comes out like a magic, basically.
That is wild. That is so wild. Oh my God.
And just an example, can you just put that back? Yeah, this is the picture we have of what Dr. Dhautri was describing. You can see there's a base, like a plate. On top of the plate, you have actually built that complex three-dimensional shape by locally fusing the powders on top of it, layer by layer. That's how it looks after built.
Very cool. Very cool. So how long does it take to print, say, the little baby Yoda that we saw on the screen a minute ago, or even that little piece, that component there? How long are we talking to make this whole process happen?
So when I was trying to look at the baby Yoda thing, I think when we were timing it, it was close to 18 hours.
Wow.
But that's because of the complex features and how much layer. We can adjust the settings to make it like in terms of how far each layer is, that just make it more rougher. But if you want it to be as smooth as possible, the distance between each layer has to be lower. So that just takes more time.
Sure.
So you can adjust a lot of process parameters for it to make the print better. But then the other end is it will take more time and material.
Right. And the timing for the metal 3D printers is also going to be in the same range, but it can change quite a bit between the two different technologies. As we walk to the other lab, we will show you the same type of metal powder bed fusion or laser based powder bed fusion, or the other one, which will be what we call as a powder injection system. So we'll show you both those systems, and which are in the research category of machines that we have in the other labs.
Okay, awesome. While you guys are walking that way, I want to ask Dr. Dhautri to talk a little bit more about the research side of things and what this could potentially mean. And I understand, Dr. Dhautri, you're not even looking at just the present, but you're looking way ahead into the future as well, and how this is going to impact technologies and our logistics and supply chain industries.
Right.
So can you kind of talk a little bit more about that for us?
Yes, I'll be glad to do that. And that's how we started our call for the support. Basically, when we went to state asking to help us to build this technology, we went with a view or vision which was based on a holistic approach to this technology, not to just we being a scientist or engineer just be passionate about the science and technology, but we were also passionate. We went with a vision of building this for the practical purposes. And what it means is as this technology is going to be into mainstream manufacturing down the road in a maybe a decade and a half to 2 decades down the road, So when it goes to mainstream manufacturing, it is not just a manufacturing component. You know that as a whole operation involves a lot more than the making the components. You need to have a raw material come into it. You need to store the raw material. You need to manage the time associated with handling the raw material. You need to also, these technologies, as you saw, that it's computer-based technology. Everything is fed into the computer and computer operates the machine. So computer-related issues, all those things are involved in these things, going to be involved in these things. So right now what happens is everybody is trying to be busy in making these components better. So they're looking into science of this technology. And nobody is thinking anything beyond that. But when we proposed this center, we thought that we are confident enough that this is going to become a mainstream manufacturing process. So we want to look into many other associated aspects with this technology, such as cybersecurity associated with this technology, logistics supply management associated with this technology when it becomes a mainstream manufacturing process, how you manage the raw material, how you manage the timing of the printing, how you efficiently keep this process going on. That's where logistics and supply management is the issue. So we are bringing the researcher from the logistics supply management side. We are bringing the people from the cybersecurity side because this is a computer-based technology. So when it goes to mainstream manufacturing, somebody can hack the technology and make it disruptive, basically try to play a bad role in it. So we want to look into that, how we can make this technology more secure when it becomes a mainstream technology. So we are looking into cybersecurity aspect of it. So a lot of faculty members, researchers are involved from the cybersecurity side, logistics, supply chain. You look at the conventional manufacturing technology, which involves several processing techniques, whereas this, and because of each processing technique, there is a different supply and logistic issues associated with each of those, and collectively there will be many more of those, whereas this technology takes the raw material, fits into the machine, and the final component comes out of that machine. So it does not have many other steps into it. So supply and logistic associated with this technology is going to be far different than the supply and logistic management associated with the current conventional manufacturing technology. And nobody knows what it would be, So we are looking into that ahead of the time, even though it is not mainstream technology. So we are putting ourselves, UNT, way ahead of the time. We don't mean that people are not going to look into this aspect of the technology, but they are right now busy into only science of this to make the components with the properties what they needed for application. Once it is made, then everybody will wake up and start thinking about cybersecurity, logistics, supply chain, and then they will start working on it. No, we are looking collectively in a holistic manner into all aspects of this technology. And that is what made us different than many other groups or the many other centers which are associated with this kind of development, and that is what I think probably state legislatures like about our holistic approach about this center,
I love that. There's nothing better than some good collaborations. And it sounds like you guys are already making that happen. And our students are only going to be better for it. So thank you for that. My gosh, I glanced at the time and I went, holy moly, we need to get on the road here. So I tell you what, let's take a look at one more machine that we have there, and then we'll bring it back and talk a little bit more about the legislative advocacy and a couple of other things before we wrap it up.
Yes, Raj.
Yes. So welcome back again to the lab. So previous lab, as we were mentioning, was based on the educational aspect, which is the Institute for Transformative and Education in Additive Manufacturing, whereas this one is more the research-oriented lab. And this has research-grade metals 3D printers. Definitely from a research perspective, we are focusing more on metals 3D printing. We are also trying to do some ceramics printing, which we'll talk about a little later. But in terms of metals 3D printing, we have two research-grade high-end equipment here. The one you're seeing on the left here is an Econity machine. That's just the name of the company. But it is based on the same principle of selective laser melting, or you might say laser powder bed fusion, just like the previous teaching machine you saw. The machine for the metals 3D printing in the teaching lab is just a lower end system. This is a much more higher end system, more dedicated for research. And that means that you have, let's put it this way, you have many more bells and whistles on this than what you had in the other system. And just to again giving you an idea of the price perspective, that one was about $250,000. This is closer to $800,000. So you're looking at a much substantially enhanced system, which has not only the ability to do the same rastering of the laser beam, and you can print in layer by layer, but it allows you to do a lot more, you might say, detailed control. Like I can control in this case how the laser beam will actually move on the surface of that powder bed that we were talking of in the previous machine. And there's a high-speed camera, which obviously is also built into this system. Again, it's difficult to see, it's kind of dark, but the high-speed camera tracks how your laser beam is moving and how the powder particles are actually getting melted inside that. So these are the type of in situ diagnostic tools that we have. We can also read the temperature of the melt pool. We are trying to do spectroscopic reading to find out what is happening in terms of the chemistry of the material that is being melted, and so on and so forth. Another unique feature of this system, again, a unique feature amongst any systems of this type, is we can heat that platform on which you're building. Now, you may ask why bother about heating? Well, one of the challenges in metals 3D printing, or the big challenges, is when you rapidly fuse the metal or melt a metal and then solidify it, you get a lot of stresses in the material. And this goes back to the question that was posed earlier: are we getting the same properties in these 3D printed metal parts as conventionally processed? And because you have so much stresses in the 3D printed metals part, it can behave very differently in its properties than the conventionally processed one. So what we can do with heating that platform is to reduce those stresses, these inbuilt stresses or inherent stresses in the material that arise from the 3D printing process. So there are more aspects, but in the interest of time, we'll probably just, unless there's questions or anything you would like to add, Mansi?
No, I was just going to show them some of these things. Components which we can print, I guess. Some of the components which we printed for show and tell, and also to show the versatility of this machine. Some of the things which we printed here are, this is printed on titanium alloy, and this actually is supposed to be like a jaw line. Somebody has a fracture. The best part, which Dr. Dhaotre and Dr. Raj touched upon earlier, is the customization of this one. So this can be very specific to every individual. So this is actually like a skull plate here, which are cranial implant, which goes on top of, like people said, the skull. These are just like the other ones, which both go on the legs. So there's a femoral implant, and in the back you have a tibial implant, and that's just like how it prints here. We have a visualization of how it prints, similar to what we showed earlier.
I think this is so fascinating, because in the news we hear all day long about how the potential is there in the medical industry and helping people at a lower cost and being more efficient and getting these components produced, I guess. And so to think that we have the ability to do that right here in Denton, Texas, and have our students learn firsthand how to give back and help is truly remarkable. So thank you for sharing that. That is really special. What is the last machine that you were going to show us there?
Yeah, so this is another type of a metals 3D printer. Again, uses raw materials that are those fine metallic powders that we saw before. And So it starts from the same metallic powders, but the main difference in this technology is that you do not have a gantry of powders or what we are calling a bed of powders, like a repository, and you just raster the laser beam, which is what happens in the previous printer. Here, you have the metallic powders that are carried from these powder feeders. As you can see, these are different feeding units, and you can take different powders. You can actually mix them. You can do whatever you want in terms of controlling their speed of flow. They're flowing through those pipes or the tubes that you can see there, and then they enter into, so you can imagine the same technology. Now you have a platform, but you don't have metallic powder on top of it. You're feeding the metallic powders, the laser beam comes down the center and then creates a local pool of liquid metal. That's called the melt pool. So the liquid metal pool is on your platform. The powder is injected or fed into the pool. And then you can move that your platform in the X and Y direction, and you can move the laser beam in along the Z axis. And using that, you can again do layer by layer deposition of the material. Couple of differences between the two in terms of the ability to handle materials. A few of the novelties of this system is you saw that there were 4 different powder feeders, which means that I can actually mix and match different metallic powders while making the same build. So I can 3D print a component. A complex shape is one thing, but not only is it a complex shape, but I can also go and tailor what is going to be the chemistry or the composition in each part of the component. That is the power of a system like this. That's one advantage that you can do. And in general, this one can print at a faster rate. So it's a faster rate of building or 3D printing compared to the powder bed fusion. Of course, it comes at a price. The price obviously is that you're not going to get as smooth a surface finish that you can get with the other one. So that's in a nutshell the basic differences. Yeah.
That makes perfect sense. So it is my understanding that if we had not made a trip down to Austin, Texas 2 years ago and taken roughly 100 students and faculty, staff, and alumni to go visit our state legislators, then CAAAM would not be in existence today. Would that be safe to say, Dr. Dahotri?
That is definitely the true thing, basically. I believe in that. I think that help us a lot to convey our message to the legislatures that we are there and we have capabilities and we have vision to do something bigger and better, and that happened with the support from the Alumni Association and all our alumni who went with us to convey this message to the legislature.
Fantastic. And as we all know, our legislators are meeting right now, and we have a small little campaign going on where we are going back and we're going to ask to continue to have the state fund our CAAAM program. Would you like to elaborate a little bit more on that?
Yeah, Miss. The thing is, we started this center after getting the approval from the legislature in September 2019 in the FY20. We started with a big enthusiasm, big vision about this center, and within 4 or 5 months we got hit with the COVID-19. And that slowed us down pretty heavily in terms of, because nothing could be done. It was nobody's fault. So what we wanted to move on with the speed, we could not, because this level of center or this intensity of center to build, it takes a lot of efforts, because we were starting from the scratch. Nothing was there. So we had to build the space. We had to buy the new equipment, then get the equipment into the center, into the space, newly built space, coordinate all these and commission the equipment and get. So it has been a pretty slow because of COVID. So we spent for most of the last year and most of this year's part into building the infrastructure, getting the equipment. But in spite of that, we have made a lot of progress. We have written a lot of external funding proposals. We got support from many other agencies to continue our research in this area. We were able to build a center space. We are able to commission many equipment. but we would like to go further, and continue building this one and achieve or complete our vision for this one. And most thing is next few years we would like to focus on the education and training part of it, which we just started doing that. We started communicating with our colleagues around in the North Texas and beyond, and currently our we are in a stage of discussion, and eventually we will set up the specific plans for these collaborations and see where we go in terms of training and educating the students, as well as training and educating the existing workforce in the industry. So we would like to have continued support in next couple of cycles of the funding to achieve our goals. Of course, as I mentioned that science and technology development wise, we are not only we, but everybody is still far away from putting this technology into mainstream manufacturing. So for that also we need support from legislature to achieve that goal.
Absolutely. And Claudia, I don't know if our general audience out there in Facebook or Zoom can see the classroom that Daniel's in right now, but ladies and gentlemen, that's why we do it. Those students right there continue to advocate for our students, and those students' parents better be really proud because they are in class when it is 20 degrees outside and potential bad weather. We are proud of you guys. Keep it up. And so not to make light of a really serious situation there, but seriously, we're very proud of those students, and we're very proud of what Dr. Dahotri and his team has built here at UNT. And if you are a parent watching right now and you've got a student trying to figure out what to do after high school, come visit the campus, come talk to us. If you are a professional in the healthcare industry, the automotive industry, whatever it may be, and you see an opportunity for a partnership here, let's talk about it, okay? Please reach out to us. We're happy to connect you with Dr. Dahotri and his team, or email Dr. Dahotri directly. I'm sure he would love to hear from you. We're constantly looking for ways to build and grow this program, and we can only do it with the help of our alumni, our parents, and our community partnerships. So Claudia, Dr. Dahotri, go right ahead, please, sir.
We are there to serve our community, we're our constituents. We are always there, Let us know how we can serve you, how we can help you. We are looking into ways and means to collaborate with people at various levels. We are ready to work with the high school students who are interested in this kind of technology, making career into this one. We are ready to work with the industry constituents, who wants to retrain and get ready for the next generation technology. We are ready to educate the students from the community colleges who wants to be enter into workforce newly, and we are ready to educate the people who are already attending the colleges and want to make the career into this new fascinating next generation technology. So let us know. We are there to work with you, and we will work with you the way you want us to help you. Feel free, come and visit us, take a look at us. We are one of the few in the nation. I'm sure that, because the kind of equipment we have, those are one of two or one of three. So that provides itself a unique opportunity for you to understand and to train yourself in this technology. So feel free to contact us. I'm glad that I already have 2 or 3 emails asking about it on my iPhone. I just replied a couple of them. So I'm glad to see the interactions, and I hope it continues that way.
Absolutely, guys. And I know there are some of you in the audience asking really remarkable questions, but sadly we are out of time. So please email Dr. Dahotri. He is a wealth of knowledge and information. And thank you again for your time. Thank you to Dr. Banerjee and Dr. Muntry for joining us. We appreciate you guys so much. This is really spectacular. All right, Claudia, it is back to you, ma'am.
Thank you all so much for being here. This is so awesome. I love I'm like baby Yoda's biggest fan. So when I saw him, I nearly had a heart attack. So that was awesome. Thank you to the CAAAM crew. And thank you, of course, to Daniel Suda, our colleague, who is our awesome cameraman on these episodes. Thank you, Daniel. Now is your last chance to check out the chat function here in Zoom for a link to this week's survey. That UNT prize pack is definitely worth winning, so make sure you're entered. Our next episode is coming up fast, and if you like live music, you won't want to miss it. On Monday, February 22nd, we'll enjoy a lunchtime concert with the one and only 1 o'clock lab band and have a chat with director and UNT alumnus Alan Baylock. To register, just check out the chat function right now or go to our website, untalumni.com/alumni live to register. Finally, now is the perfect time to join the UNT Alumni Association. Your membership helps fund scholarships for current students and incredible resources for alumni. To join today, just go to untalumni.com/join. Thank you for being here with us today, and we hope we'll see you on February 26th.